Right. Hi, everybody, and thanks for being here today. Guess my co-organizers also couldn't be here for the day today, so I will have I guess, I'll have to introduce myself for this talk. So today's talk will be about canonical foliations of bubble sheets and a spectral geometric approach to them. As usual, don't hesitate to unmute yourself and ask questions if you have any questions during the talk, or to write them in the chat. I think I will see the chat to monitor the questions, but if I don't see it and there's questions in the chat and someone can relay them to me, I would appreciate. And otherwise, well, let me start this without. Let me start with stating what the theorem of the day is. And so here it is in all its technical glory. Saying that if I have here my manifold will be a product of Rk and Sn minus k, and a metric that will be sufficiently close to the standard metric, then I can uniquely foliate that manifold with graphical spheres that have quasi-parallel mean curvature. And now, okay, this is quite a mouthful as a theorem, and I will have to explain to you today what does it mean to have quasi-parallel mean curvature, and also, of course, why do we care about this, and what do we mean by sufficiently close. And let me start this by this I guess apocryphal quote that I've seen attributed to André Weil, or at least that's what my differential geometry professor, when I was learning this, was telling us it came from, who was telling us that geometric information will reveal itself in invariant form, and that imposing a set of coordinates is doing violence to the mathematics. Now, I say André Weil maybe because that's what who the quote was attributed to, but when I was looking for a reference, I couldn't end up finding it, so I guess it's apocryphal. But nevertheless, this is a general feeling that anyone who does um, differential geometry or Riemannian geometry will have as a feeling somehow that coordinates are often crutches that allow us to make certain computations, but that might obscure some of the important behavior that we're looking for, and that may obscure the actual, intrinsic and geometric reason why a given result is true. However, it happens pretty often that that special choices of coordinates will reveal particular features of the geometry at hand, and these special choices of coordinates, normally you would have to make the choice of them in a geometrically relevant way, in a canonical way. You have to not have too much choices about how you make them if you want them to reveal the features of your choice. And let me give you an example of such a set of coordinates that anyone who does a differential geometry class learns about quite quickly. And these are the geodesic normal coordinates, where basically what you want to do is you want to have a chart that goes on your manifold that will map your that will map the circle according to straight lines to an open set on your manifold according to geodesics that you would follow. And if you use that map to define coordinates, the metric will read in the following way. So your metric at x, a point in the disk of radius 0, will look like the Euclidean metric plus a correction that will be, and this is what's important here, this correction here is of order 2, and then lower order terms, okay? And so what this means is that by using geodesic normal coordinates, we can see that not only is a manifold an object that locally resembles Euclidean space, one can arrange it so that it locally resembles Euclidean space to second order. And it does tell us even more than that. What is the coefficient here? So this is the curvature. And these coordinates will tell us also this somewhat maybe intuitive property that this deviation at second order from the Euclidean space is completely governed by the curvature of our manifold. And it is not the case that in any old coordinates the metric will look like this. In most choices of coordinates we will have first order terms, but we can make a specific choice that will reveal exactly in which way is the space that we're looking at Euclidean. Yeah, so this is what I was saying. And so this is what we will generalize. And most coordinate systems that we look at are foliations in some sense, right? You can view the Euclidean coordinate system as foliating R2 by straight vertical straight lines indexed by the x coordinate, or in general, you can view polar coordinates, okay, as a foliating Euclidean space by a degenerate family. It's degenerate at 0 of spheres that will grow and grow. And in general, basically, we would like to understand a description of our space by using simpler submanifolds that we will vary across the surface. Now, these are pretty trivial examples, but these sort of ideas can easily come from more complicated situations. And let me give you one such more complicated situation in using foliations to in Hamilton and Perelman's approach to geometrization in solving the Poincaré conjecture. So Poincaré's conjecture states that every three-dimensional topological manifold, which is closed, connected, and has trivial fundamental group, is homeomorphic to the three-dimensional sphere. And in a way, this is the base case in extending to dimension 3 the classical classification of surfaces result, which in the base case tells you that if the fundamental group of a closed surface is trivial, then it's the two-sphere. And in fact is the base case in Thurston's geometrization conjecture, which was about classifying the possible three manifolds. Now, here, let me tell you how the proof of Poincaré's conjecture that Hamilton and Perelman proposed rods. Okay, and so basically the idea is you start with some, I mean, okay, this drawing is not how you want to think about it. You want to start with maybe some sort of complicated thing that you believe might be homeomorphic to a three-sphere. You run the Ricci flow on this. And when you run the Ricci flow on this, two choices might happen. Either it will end up shrinking on itself to something that will have positive curvature everywhere, and this we end up being able to show is a three-sphere. So homeomorphic to three-sphere. Or the other option, so basically we wait until a singular region starts forming. If this region is everything, this is a three-sphere, and this is a case where you degenerate to something like this. Or the other option is that it will look like something that has a very thin neck and otherwise connects in ways that we don't necessarily see behind. But this thin neck here, okay, is a region that has very high curvature. And one of the very hard part of this proof is showing that what can happen is either having this neck or degenerating to the whole manifold. There's no sort of strands that can come out of your manifold. Now, if you have this neck, okay, that has very high curvature, what you want to do is you want to cut this neck at two parts, remove it, and cap off both sides of this with a disk and restart the flow. And this second part will basically look like a cylinder that you hope will collapse to one thing. And the idea is to repeat this finitely many times. It's a hard part of the proof to show that this process cannot go on infinitely many times and then rebuild a manifold from the pieces. And what I want to focus on right now is this part here, because the reason why you want to cut this neck is you want to kill off the region where the curvature is high and restart with a manifold that hasn't yet developed the singularities. You can show that the only way the singularities can develop is by sending the curvature to infinity. But you want that when you re-glue these cap to cut it off, you do it in a way that doesn't increase curvature, that lets curvature remain bounded. And the idea is that you need to cut your neck and do this surgery procedure in a very careful way to ensure that you haven't made the analytic situation worse by doing this. Okay, and this is what the theorem of Hamilton is that you can foliate basically a cylinder of Sn minus 1, which is what he called these neck singularities, when your metric G is sufficiently close to the standard metric by graphical spheres with constant mean curvature. So the idea is that these neck singularities that we've seen before, if we rescale them so that the radius of the neck is of size about 1, so you basically divide by the mean curvature, then in some sense, this blow up will look like a cylinder where the metric is in fact close at distance 1 over the mean curvature before the blow up to the standard metric. And this uniqueness is quantitative. Nearby metrics have nearby foliations, and those spheres are nearly round. You can make actually precise how much of a deviation from a round sphere are any of these spheres, and the result can also be stated in a purely local manner. So I don't have to have the whole of R cross Sn minus 1. I can have a large cylinder, okay, and this result will also apply. And so basically, the result is if I have a large cylinder like this, and this cylinder is not very far from being Euclidean, well, I can find a set of transversal spheres like this that will foliate along the x-axis my cylinder, and all of these spheres here have constant mean curvature. And basically, what there seems to be a question. So there's the question of what's a graphical sphere. Thanks, Danielle, for this quick question. So n minus 1 is graphical, or rather a sphere if I can write it as so let's say my sphere is sigma. If sigma is u of omega in R cross Sn minus 1 for u from Sn minus 1 to R. So basically, it's the graph of some function over the sphere. Okay, so in a way, this means that I won't end up having some of my foliation will not be bizarre, where some of my spheres end up being horizontal like this. They're all vertical. But thanks, Daniel, for the question. So yeah, this sort of horizontal sphere is not allowed in the foliation. Basically, the foliation looks like what you would expect it to look like. Okay, and in a way, this result, when you state it just like that, it doesn't look very surprising. I tell you, you have, if the metric is the standard metric, then you do have such a foliation by round spheres, which are not only constant mean curvature, they're actually minimal. Okay, minimal surfaces, meaning that their mean curvature is 0. And so, in a way, we shouldn't be very surprised about this result. However, originally, the first attempt to prove this was to find this foliation by spheres which were minimal and therefore had mean curvature 0. So we wanted to do things with a 0 mean curvature, but this ends up being impossible. This ends up being impossible because generically, Riemannian manifolds are what is called bumpy. And bumpy means that any minimal submanifold is stable. And stability of a minimal submanifold means in particular that they are isolated, which means I cannot have a foliation by these isolated stable submanifold, because otherwise the translation along my foliation would provide me one instability direction. Okay, and you can show that a dense open set of Riemannian manifold has this bumpiness property, and therefore and in any neighborhood of the standard metric, most most metrics will not have this foliation by minimal surfaces. And basically, the really important contribution of this theorem is that the constant mean curvature condition is sufficient to obtain that foliation. Now, if I go back here, or at least I'll use this for my drawings. Okay, so the idea in terms of proceeding with the surgery is that I will choose 2 points on this cylinder, and I will cut along. So this is a leaf of constant mean curvature. Okay. And this is what I will cut along. And the fact that these are constant mean curvature and satisfy some elliptic equation is precisely what will give me the estimates that would allow someone to glue a cap on each case on each side and still satisfy all the and not have increased the curvature too much. And this is why we care about this. All right. And the point is that even though constant mean curvature is not as good as minimal surfaces, in many ways it's still good enough. And so this is this is one of the major ideas in being able to run geometric flows with surgery, or at least a Ricci flow with surgery. And when things like next singularities are your only possible types of singularities, this is good enough. The problem is that so the statement that the only singularities that can happen are next singularities is true in dimension 3 for when you run the Ricci flow, but it's not true in general. It's not true in general, and for more complicated singularities, we don't necessarily have this foliation at this point. So next singularities blow up to R cross Sn minus 1 with a metric close to G0, whereas bubblesheet singularities will blow up to Rk cross Sn minus k with a metric close to G0 with k strictly greater than 2. Technically, the proofs I will provide today also work for k equals 1, but it's just not new in this case. And now, how do I interpret mean curvature? Well, the mean curvature of one of the embedded spheres is a section of its normal bundle. And this is characterized pointwise because the fibers are one-dimensional. And in this case, we live in the orientable world here. This is two-sided. So I can characterize the mean curvature by only the length of this section in the normal bundle. And in a way that means that the notion of having constant mean curvature fully makes sense. And it's not completely clear what constant mean curvature means for a section of the normal bundle to Sn minus k. In this case, the fibers are k-dimensional. The bundle itself might not be trivial. I need, talking about a vector being constant here when it's not just characterized by its length means understanding precisely how the parallel transport would work on that bundle. And so talking about constant mean curvature is not exactly what I want to do. And so the question arises in codimension greater or equal to 2, what does it mean to say that a submanifold have constant mean curvature? So my first step is I want to produce a foliation of these bubble sheets by objects that have constant mean curvature. And if I want to do that, well, I should define the concept properly first. And so the idea will be to go from what we called constant mean curvature to a different condition that is called parallel mean curvature. So let's start with some Riemannian manifold M and sigma, a compact submanifold of it that will have normal bundle n of sigma. And the metric on my normal bundle and sigma will induce a connection that I will denote nabla perpendicular, because it's a connection in the normal direction to the boundary, and therefore it also induces a Laplacian. Okay, so finally we get back to objects that we're all used to. So a Laplacian delta pub that is given by more or less the divergence of this intrinsic gradient. So this you really want to interpret this. So you want to interpret this as div. And when this normal section, the normal bundle is a line bundle, the kernel of this normal Laplacian is the constant sections, specifically, and therefore having constant mean curvature. So in other ways, constant mean curvature is the same thing as saying that the normal Laplacian of H, so this H here, that's the mean curvature, is 0. And being a line bundle is specifically means the fiber are dimension 1. In other words, sigma is a hypersurface in M. In general, it is the parallel sections that are in the kernel of this normal Laplacian. And because sigma is compact, in this situation, the kernel of this normal Laplacian is exactly the same as the kernel of the connection. So, and that's why we say they're parallel. If I try to transport that section along geodesics in sigma, there will be no monodromy. I will be able to bring back normal vectors to their origin by moving them around. And so we will be looking for some manifolds with parallel mean curvature, meaning again that the normal Laplacian of H is 0. Okay. And, you know, at this point, it seems like it should be pretty straightforward. And that just like I was able to find constant mean curvature, well, I just had to find the right definition of what it means to have constant mean curvature. I have parallel mean curvature, and I will be able to find manifolds with parallel mean curvature in the same way. However, it's not so simple. And the reason why it's not so simple is that if the codimension of sigma is greater or equal than 2, the kernel of this normal Laplacian might be trivial. Okay, and in fact, so the fact that constant functions are in the kernel of the Laplacian, something that anyone who works with a Laplacian on function is very used to, is a feature that's very specific to the fact that it's a one-dimensional vector bundle on which we have this connection. Laplacians on more general bundles do not exhibit that property, that the kernel is always non-trivial. And in fact, we expect that most submanifolds will have a trivial kernel for their normal Laplacian. So do these exist? And I mean, of course, submanifolds with parallel mean curvature do exist. In particular, with the round metric, my foliation by actual round spheres in the standard metric is an example. But given any metric, will I always be able to find such a submanifold? Now that's the question. And we prove, in fact, that this parallel mean curvature, okay, well, isn't always possible, and that we can find metrics arbitrarily close to the Euclidean metric, where you have no foliations by parallel circles in this case. So it's R2 cross S1 is the lowest dimension possible of bubble sheets. And for this example, we end up proving that we don't have a choice but to find something more flexible than parallel mean curvatures would be. And the idea of the proof is to find, basically you take a Berger metric on S3, which is a metric built from the Hopf fibration, where some of the circle fibers will be will shrink down to a point in that metric. And if you cut off a small disk from an S3 with the Berger metric, you can view this as a subset of R2 cross S1 and put a metric on this R2 cross S1 that will resemble in a large open set to the Berger metric on this S3. And if you choose the parameter, the Berger metric comes with a parameter. If you choose this parameter well, you can also make this metric be close in, say, C10 norm, if you want, to the Euclidean metric, or the standard metric on R2 cross S1. Now, you can show that the normal Laplacian, and this is just a direct computation, that the normal Laplacian on circles that are close to horizontal in or vertical, given the drawings I've made, I should say vertical here, has trivial kernel, and this is simply a computation that you can make. And then once you have this, you perturb the metric that you get to a bumpy metric, and we've seen before that bumpy metrics are generic. And this will tell me I have no minimal foliation. So a minimal foliation is a foliation by things that are in the kernel of the Laplacian. And that are not only the kernel of the Laplacian, but where the mean curvature is 0. So minimal here means h is 0, which, of course, would be in the kernel of the Laplacian regardless of its triviality. But this property, this is an open property. So if I'm close to something where the Laplacian has trivial kernel, well, I still have trivial kernel, and therefore these bumpy metrics here will not be able to enjoy a foliation by parallel mean curvature, by spheres that have parallel mean curvature, because the kernel of the Laplacian is trivial and there's only isolated minimal submanifolds. Before telling you how we solve this conundrum, let me describe a few of the properties of this normal Laplacian on the normal bundle of sigma. So first of all, it has discrete eigenvalues that will accumulate only at infinity. And this is just from general nonsense about being an elliptic operator on self-adjoint and positive on a vector bundle. The eigenvalue 0 has multiplicity at most k, which is the codimension of sigma in this story. And generically, sorry, you expect every eigenvalue to be simple. But if you take the round sphere, so here in Rk cross Sn minus k with the standard metric, then here this time 0 has multiplicity k, and then the next eigenvalue is equal to n minus k. Okay, so you have a very clear separation between the first k0 eigenvalues and the k plus first eigenvalue. So even without this genericity statement, in a neighborhood of the standard metric, it is the case that you have this strict inequality here between lambda k and lambda k plus 1. And yeah, so and in fact, not only is it smaller, it's in fact quite far from lambda k plus 1 in a small enough neighborhood, at least n minus k apart. And so I will use these facts to define the condition that I call quasi-parallel mean curvature. So let's put p lambda to be the projection on the eigenspace of the normal Laplacian with eigenvalue lambda. And I define the operator q to be the sum over all lambdas that are strictly smaller than lambda k plus 1, and of course lambda in the spectrum of this normal Laplacian of these p lambdas. So generically, this will have rank k, and I will call a section of the normal bundle quasi-parallel if it lies in the image of Q. That is, if 1 minus Q applied to S is 0. And the important thing is that generically and in a neighborhood of G0, the dimension of the image of Q is exactly K. And this is this image has constant dimension, unlike the kernel of the normal Laplacian. Now, one of the things that you may notice is that this definition doesn't use at all the fact that I'm looking at the normal bundle. And I would define I would define a section to be quasi-parallel for any vector bundle in the exact same way. That is, given a vector bundle whose fibers have dimension m, then if you're in the eigenspace corresponding to, or in the sum of the eigenspaces corresponding to eigenvalues smaller than lambda m plus 1, then you are quasi-parallel. In a way, this is saying that I want the largest dimension possible of a space that will provide me with a frame for my bundle. I want the largest possible dimension for that. And I want to be as close as possible to be parallel, where parallel means being in the kernel of the Laplacian. And as close as possible in this sense means belonging to the first, to the eigenspaces of the first k eigenvalues. And so we arrive at our main theorem, which is that if we have a smooth metric on a bubble sheet, and again, these bubble sheets appear as the blow-up model for singularities in mean curvature flow for submanifolds of dimension at least 3 of Euclidean space, and for Ricci flow for manifolds of dimension at least 4. So this is one of the most prevalent types of singularities. And what I show is that whenever the metric is close enough to G0 in some specific spaces, I can find a unique smooth foliation by embedded graphical spheres. Each of them has quasi-parallel mean curvature and will be close in some sort of in the CL gamma norm to the actual round sphere. And again, this closeness is in the fact that if I'm U of omega, then it's in the distance between this U and the constant U equal to Z. So again, there is a local version of this theorem. So if I have a very large, if instead of having RK here, I have a large disk instead, or I mean just a disk instead cross Sn minus K. So if I have a disk here, the result still holds. Is also okay. Nearby metrics have nearby foliations. If if two metrics agree on some open set, the foliations agree on that open set. You have whatever you want there. And how the proof goes. Oh no! Before telling you how the proof goes, let me state a corollary. And basically, it's the corollary that resembles the one where for Ricci flow, if eventually I look like something where everywhere is singular, it means I'm close to a sphere, close to a point. And basically, in this case, it means that if I evolve my mean curvature flow and eventually I'm singular everywhere, I'm in fact collapsing to the neighborhood of some manifolds. So I'm more or less this thing here, where I'm collapsing to this neighborhood of my of A given some manifold. And the idea for this is that if I'm everywhere singular at the same time, then this foliation will have no choice but to agree on the intersections of any cover of that manifold. And because they have to agree, they will connect in something that will end up looking like a global foliation. And this global foliation by graphical spheres is precisely isotopic to a neighborhood of this closed K manifold. And so, in a way, this is a first step towards understanding what can be the global topological features of singularities of geometric flows like the mean curvature flow and the Ricci flow in higher dimension. Because I mean, we're starting to understand what are these local models, for example, the bubble sheets, for example, the next, there's a few other ones, but we need to be also able to talk about the global features. So let me discuss briefly an idea of the proof. And the first one will be to, if I'm looking at graphical spheres, I will, whenever I have I can replace my parameterization of functions of spheres by functions over the sphere, and I'll take a frame for my normal bundle to this sigma u, and I'll state that if the metrics are closed and the norm of this u is small, then applying my operator Q to this frame is still a global frame. And then you pose this function that will go from the space of metrics times functions, which is given by this formula here, which the important part to notice is that this is quasi-parallel if and only if, because this is a frame, if and only if this J is 0. And in particular, at the standard metric at 0, it's 0. So I can, I want to understand basically the set of metrics and functions U where this J is 0. Now, and the idea is to use the implicit function theorem to tell me that in a neighborhood of 0, I will be always able to find to invert this this J. Now the problem is that the linearization of this J is the Laplacian, and here this is really a matrix with k Laplacians on the diagonal, which has a k-dimensional kernel and co-kernel that consists of the constant maps. And we specifically build J so that it has image in the mean zero functions, and restricted to that space, the linearization is invertible. And by inverting this linearization, this gives me a quasi-parallel mean curvature graphical sphere over 0. And because they're mean 0, if I solve the problem by moving around the point at which I start rather than starting at 0, this gives me precisely the foliation by graphical spheres with quasi-parallel mean curvature, and the invertibility of J is what ends up guaranteeing the uniqueness. Okay, so what do we want to do with this? Well, our goal is to, so the ultimate goal is to develop surgery for bubble sheets. So I want to develop surgery for bubble sheets, which means how can I cut the bubble sheet once once it appears, in order to remove this high curvature region. Now, when I had a cylinder, this was, I mean, certainly not trivial, but one of the important part is that choosing these 2 points here is basically choosing the endpoints of an interval 0 to L. Now, in general here, if I want to proceed with this surgery, rather than choosing the endpoints of an interval, I will have to choose appropriately a curve. A curve inside my bubble sheet to cut across. And now the problem is that regluing a disk there, this is an operation called a Dane filling, and you get really different things at the end that depend on the way that this curve along which you have cut was knotted inside your larger manifold. So the point, I guess, here is that there's still big obstructions to continuing the program of performing geometric flows with surgery when the singularities are more complex than the next singularities. However, our results provide what we think are an important first step in order to understand this, because prior to this, we didn't even have a good way to describe the geometry and even in any way the global topology of any of these bubble sheet singularities. And this is where I will stop Thank you very much. And I guess as I chair my own talk, I will take questions if you have any. All right. Well, I hope that you still managed to get something out of this talk and that it was just really clear enough. I'll see you all next week for the next edition of the seminar.